On the left-hand side, there are a number of different buttons. Right now, by default, this button at the top where you see the folder is depressed. So this is looking into my local laptop directory. So this is my home directory, and my home directory is C users Jamian. So it's looking into my C drive, users directory, Jamian, and I've got a whole bunch of different files and folders in there. However, you can also connect Mo to something called Silo. Silo is another product that we developed. It's a protein repository. It allows you to query large protein databases, very similar to the RCSB. But in addition to that, what you can do is you can append your own custom crystal structures as well to it. And there are advanced query methods that allow you to query your database to search for 3D interactions, pocket similarity, and so forth. We also connect to the RCSB directly, so you don't need to go to the RCSB website to download a particular PDB code. You can see that the RCSB right now has over 200,000 structures right now. But if you just type in the code, for example, today we're going to be working with 1M17, it'll filter and it'll show you only the code that has 1M17. If I just wrote 1M1, it will filter out all the structures that have 1M1. So that's about 33 structures out of the 200,000. The last button right here, this allows you to connect Mo to your internal databases. So a number of institutions have their own cryo-EM facilities or crystallographic support, and you generate a lot of structures. So all the databases that house all your structures, you can actually connect directly and access it through the open panel. Today, I'm just going to focus on my local directory. I'm going to click on the star here and navigate to $mo sample mol. $mo means your Mo installation folder. When you install Mo on your computer, it's going to be installed on your C directory in a folder called Mo 2022. That's what $mo refers to. And the sample mol, which are subdirectories, house a number of different files and folders that we use for courses and tutorials and so forth. So right now, given the fact that I'm doing the structure-based design and ligand modification course, we have the file already prepared, well, not prepared, but downloaded. So what we're going to do is we're going to load it directly from that directory. So you'll just select it, click OK. This will open up the Load PDB File panel. And this panel, before loading your structure up within the Mo environment, allows you to load your structure either in the form of the way, load your structure in different definitions. So what I mean by that is either the biomolecule assembly or Contax 4.5. So for example, Contax 4.5 would mean loading up your structure with the adjacent protein contacts that are 4.5 angstroms away or 10 angstroms away from your protein that you're loading up. Yeah, I believe we have a question from Rana. You want to go ahead and ask your question?
Yeah, I noticed that the file that you are loading has the format of .pdb.gz.
Yes.
The structures that I had before only had the format .pdb, I guess.
Yes. Yes.
What
Yeah. So
GZ stand for?
Yeah. So the GZ is just a zipped compressed folder. And the reason why we do that, let me just go back to it very quickly here so that people can also see what you're referring to. So if I go back to my open panel and I navigate to my $mo sample directory, you'll notice that it's 1m17.pdb. Usually when you go to the RCSB website and you're downloading it, you'll have the option to download it as a .pdb file or a .pdb.gz file. What the GZ stands for is a compression method. You can think of it as a .zip file or a .tar file. It's when you have a large file and you want to compress it, you use an archiver to compress that. That's what it refers to. And the reason why we have all the files within the Mo environment gzip is because we want to make the footprint of Mo on your laptop or on your server very light. We don't want to take up too much memory. So that's why we zip them. Does that answer your question? Okay. All right, so let's get back to the load PDB file right here. So when this panel opens up, you have a number of options in terms of loading your structure. You can open it up in terms of the biomolecule assembly. So this is a definition given to it by the PDB file. You can load it up with context 4.5. So as I mentioned, it's 4.5 angstroms. So all the residues from the adjacent protein up to 4.5 angstroms that will appear when you load it up. You also have an option that almost 10 angstroms away. Now, the reason why you would want to load structures, your protein structure with the adjacent protein contacts is because, for example, if your protein has a lot of disordered loops, or it may have even ordered loops, you want to see if there's a certain bias during the crystallization process that's taking place where the conformation of your loop or your ligand binding or even your macrocycle binding on the surface of your protein is somehow being affected by the adjacent protein. So if you have two proteins that are very in proximity to each other and your, let's say your molecule, your macrocycle is bound on the surface of the protein, but contacting both protein crystal structures, that tells you that there might be a bias. You should take that into consideration, and that you should further investigate to see whether or not in free solution that particular protein would adopt that particular conformational state. So those are things that you can do in MOE when loading up your structure. The other thing that you can also do is load up alternates. Sometimes what ends up happening is that when when the crystallographer is generating your crystal model or your cryo-EM model, the electron density that you have may not be very well resolved, or maybe quite large and can accommodate your ligand in multiple different conformational states. And so what's customary is the crystallographer or the person who is elucidating the structure will also input or add alternate conformational states for that particular fragment and so forth on your ligand. So that's also an option that you have in this load PDB panel to load up those structures. Today, I'm just going to leave the default settings. I'm not going to complicate the situation, and I'm just going to click OK. So that'll load up the structure. So there we go. Now, just to make it easier on the eyes, given the fact that this is a black background, I typically like to switch that to standard white. And you can do that through this button right here. So you'll notice that when I click on it, in your standard MOE, you won't have all this many options. You can see I've got many different themes that I've generated using this. So in MOE, what you can do is once you set up your visualization, you can save that particular theme and you can always refer to it. You don't need to redecorate or change all the visualization parameters. You can save that through the visualization setup. And the way that's done is through the visualization setup panel. But that's a little bit beyond the scope of today's discussion. But just for you to know that through this panel, you can change, for example, the light, the lighting, the material, the background. You can change the text effects, the molecule thickness, ribbon, the interaction states, and so forth. All right, so you have complete access to it from here. Today, I'm just going to leave the standard white setting, keep it simple so that everybody can see what's going on without any distractions. All right, so we've loaded the structure up. The first time you load up a structure, you'll notice that your structure will be in ribbon format. And if it has a ligand, the ligand will also be displayed in this thick cylinder form right here. So you see the ligand that's bound. Now, the ribbon has some annotations to it. So the way we do this is all the alpha helices are annotated in red, the beta sheets are in yellow, the ordered loops are in blue, and the disordered regions are in white. All right. Now, the first time when you load up the structure, you can't just take the structure and run a docking calculation. It's just not ready for any type of simulation to be run on the protein. And I'll explain why. Whenever we're generating a crystal structure, typically the resolution at which we develop or elucidate these structures, they're not good enough to capture the coordinates of hydrogen. So this structure right now doesn't have any hydrogen information. We don't have any protonation states or anything of that type. The other thing is the atoms don't have any charge, so those need to be charged. And in some cases, you might even be missing heavy atoms, or you might be missing loops. Now, if you look at this protein, and the reason why I picked this example is because it's obvious. Over here, you can see that there's this disordered loop, and then there's some type of a break, and then there's this squiggly ribbon that's kind of hanging out in space. Well, in reality, this is actually connected to the structure, to this kinase. But the problem is that this is broken. That means it doesn't have any 3D coordinates. And the reason for this, it's because if you look at the electron density of this structure, you'll notice that there won't be any electron density coverage in this region. And if there isn't any electron density, the person, the crystallographer in this case, who was elucidating the structure will not be able to model in the coordinates for it. There's no experimental evidence for it. And so he doesn't want to take the chance and just generate one. What we need to do is we need to model that particular loop if it is of interest, or maybe neutralize the ends, both the C and N terminus, and then kind of move on. Now, all this requires preparation, and MOE has a number of tools that allow you to do that. There's the quick way, and there's really the granular, detailed way where you can inspect each of the different elements, and you can prepare them to your liking. So I'm going to show you the detailed way so I can expose you to some of those applications, and then we'll prepare it using the quick way. So the first thing that you need to do, as I mentioned, when you load up a structure, is to prepare the structure. It's paramount. If you don't prepare the structure, any downstream calculations that you do are completely useless, all right? Because the numbers that you will generate in terms of docking score or protein property calculations are irrelevant. They don't represent the full integrity of the protein. So to prepare the structure, what we'll do is we'll go to Compute, we'll click Prepare, and select Structure Preparation. That will open this panel right here. In this panel, it tells you, for example, it's divided in two sections. There's this top section right here. So this is essentially what you're looking at. So right now I'm looking at my structure called 1M17, and I'm displaying the issues. These are the heavy atom issues that are present within my system. Those issues are listed in the table right here. You can see that I've got, for example, some topology hybridization issues. If I go down here, you'll see there's a break, tap, 12 loop, histidine 964 to leucine 977. So there's a 12 residue loop between histidine to leucine that is broken. And that, of course, refers to this area. How do I know this? Well, if you click on it, it will actually focus the attention. See, it hides the rest of the protein. It doesn't delete it. It just hides it. And it focuses the attention to that broken region. So there's my leucine, and there's my histidine, and there's a break within this region. Now, the sequence is known. It's just that there aren't any 3D coordinates. Now, to visualize, to ensure that we know the sequence, we need to look at the protein sequence itself, because we're just looking at the atomic coordinates right now. To visualize the sequence, we need the sequence editor, and that could be accessed through the SEQ button right here at the top. So if I click on this, the sequence editor opens up. And the first time that you open up the sequence editor, it will actually look like this. So it will be in 3-letter code, and then you would have to horizontally scroll your scroll bar to visualize all the sequences. But I don't like that. So usually what I do is I can change the 3-letter code to single-letter code by clicking on this K-Lyse button at the footer of the sequence editor. And then I can also wrap the sequence by clicking on this little arrow right here, and that will wrap it. That way I don't have to horizontally scroll. Now, if I look at where this is situated, so the way we can do that is if I just go and select the residue, so I can click on the ribbon, and then if I shift click on the ribbon on the other side, it will select both of the residues. And everything is synchronized in MOE. So if you select in the MOE window, it will also select in the sequence editor. So there's my histidine, and there is my leucine right there. All right, let me enlarge this so you can see it a little bit better. So we'll go down. So there it is. There's the histidine and there's the leucine. I'm going to deselect. Notice that between the histidine and the leucine, there are a bunch of residues. This is the sequence. This is the connection, but those residues don't have any atomic coordinates. So what we need to do is we need to model those in, or we'll tell MOE, you know what? This area is not of interest because it's not in proximity to the active site. So it's not going to disturb us. So you can cap it, you can neutralize it and not build the loop. You can do that as well. You'll notice that in the structure preparation, the option right now, in terms of preparing this, is to cap it. And if you look at down here, it says cap. You have a number of options. You can build loop, you could charge it, you can cap it, you can say, MOE, do it automatically. But MOE chose to cap it. The reason why it's capping it, it's because the number of residues that are missing between the histidine and the leucine are 12 residues. And building very large loops that have 12 residues cannot be done reliably. It requires some input from the user to model those in, because there are many solutions. The environment around this loop is not really contained. It's out in space. So that means that you can build a loop this way, you can build a loop the other way, you can build a loop on the distal side. So there are many different solutions to it. So what MOE chooses to do is to take a conservative approach, and it says, I'm going to cap it if your active site is very far away. It's really up to you to say, to come in and say, all right, the loop is important because it is in proximity to my active site. Maybe I need to build it. Now, you'll also notice something else if I go into the sequence editor. So if I deselect, you'll notice that right next to the H, there's a fine line, and then the font weight of the H versus the L and the residues that are missing are slightly different. All the residues that have atomic coordinates are bolded, and the residues that don't have any atomic coordinates are not bolded. So when you're looking at a sequence, you'll know very quickly which part of your sequence doesn't have any atoms within the 3D visualizer and which ones do. The ones that are bolded have atomic coordinates. All right. All right. So this is just a brief discussion of all the issues that need to be corrected within the MOE environment. Now, the other thing that's missing are protons. So if I click on protonation state right here, these are all the residues that are missing hydrogens that need to be added. Now, you can manually go in here and click on aspartate. It'll take you to aspartate, and you can inspect it. And then you can say, all right, well, is this aspartate exposed to solvent? Is it internal to my protein? Do I want to protonate this? Do I want to keep it as the negatively charged carboxylate? You can decide exactly which state you want to apply by clicking on state. These are all the different states that you can apply. There's the negatively charged, the carbonyl pointing in this direction, or the carbonyl pointing in the other direction. So there are multiple states, and you can go and individually inspect that, but that would be quite cumbersome. You've got, I would say, a few hundred residues right here. You're not going to click each one and evaluate them. So to automatically protonate the system, there is a special application that does that. It's called Protonate 3D. And this will protonate your system under default settings of 300 Kelvin, pH 7 with a salt concentration of 0.1. If you click OK, it will initiate and it will automatically protonate everything. Now, both of these two applications are really at the pillar of preparing your structure. Both the structure preparation and the Protonate 3D are important applications in preparation of your protein complex. But we're not going to use either of these structures. Instead, what we're going to do is, after we open a file, if there's another button right below it called Quick Prep. If you click on this, this is the panel that opens up. I'm going to leave the default settings. I'm going to click OK, and this is going to initiate the preparation process. So for a protein structure of this size, it will typically take about 90 seconds to prepare your full protein so that you can start your modeling session. So it really depends on how you want to prepare your protein. Do you want to go in and inspect and visualize and really evaluate? Or do you want to allow MOE to prepare it for you in about 90 seconds, and then you can go about running your docking application or calculating your protein properties? So as the calculation is running, you can see at the top right here, it's correcting the structure right now. It's called the homology modeler to generate some and fix some heavy atom topologies that you've got issues with. So let me just describe to you exactly what's going on. This panel is actually broken up into 3 sections. There's the preparation, there's what's called tethering and fixing, and then there's energy minimization. So at the top right here in the preparation, it calls the applications that I just showed you right now, the structure preparation panel and the Proteinate 3D panel. And it does this in sequence. So it fixes all the heavy atom issues. And once it has modeled in all the heavy atoms, then it will add the hydrogens, protonate the system, charge it. And that's this step. The next thing that it's going to do right here is it's going to tether and fix some of the atoms. Tethering means that for each of the atoms that are within your protein environment, for example, like this atom right here, it will apply a force constant. There's a strong force that it will use to hold that atom in position, all right? And that force is defined by a certain strength. So right now, the strength is 10. These are dimensionless units, and 10 is a weak force. 1,000 would be a very strong force. That means that there isn't a lot of room for movement if you apply a force of 1,000, let's say, right here. The reason why you want to tether your structure is because in the next step, when you apply refinement means energy minimization. You're going to relax your protein. You don't want your structure to perturb too much from its original coordinates, at least for the receptor. And that's why only the receptor is enabled. You can see that the ligand and solvent atoms are free. They're not tethered right now. Only the receptor one will be. It's really not to perturb the original coordinates. That's why we apply that force constant. And of course, the reason why we apply an energy minimization, it's because when we're generating or elucidating structures at first, there might be some inherent strain or clashing interactions that might be present in that crystal structure or that cryo-EM structure. And what we want to do is we want to alleviate some of that strain or clashing interactions. All right. You can see that the preparation is already done. It's finished, and we can start our modeling process right now. All right. Now, the first thing that we're going to do is we're going to evaluate the structure and the active site, the ligand active site. Now, you'll notice that I'm kind of rotating this protein around or translating it, and you might be asking yourself, well, how do you do that? Well, to rotate or orbit the structure, you click the middle mouse button. So I highly advise you have a 3-button mouse when you're using MOE. So a left click, a middle, clickable scroll wheel, and a left click. So with the scroll wheel that's clickable, you can rotate it. And if you shift and middle mouse click, you will translate it. If you don't have this, there is an alternate. It's the soccer wheel down here. You'll notice that the soccer wheel right now has this circular arrow. If I just left click, it will orbit it. All right. And you can move the mouse away off the soccer ball. As long as it's depressed, it will still rotate. And if you click on the circular arrow right here, it'll change to a crosshair. That will allow you to translate. All right. So these are some of the MOE mouse functions. To select, you just need to left click. You can select ribbons in MOE. You can also select atoms in MOE. All right, so if you want to do multiple selections, it's shift left click, and it will select multiple selections. You can also click and drag a box to select everything within a box. If you don't remember any of these mouse controls, it's not a problem. Just go to help and then click on mouse, and that will show you the mouse reference for the MOE window. Right now, the MOE window, viewing system, these are the controls. For selecting atoms, these are the controls. For moving selected atoms, these are the controls for the MOE window. MOE has three major windows. It has the MOE window, it has the sequence editor, which we used, right? This was the sequence editor. And it has something called the database viewer. We're going to get to the database viewer a little bit later on in today's session. But you can refer to the database viewer and all the options down here, the sequence editor and all the options, and the MOE window. All right, so it's, again, help, mouse. All right. Now, the next thing I also want to kind of introduce you to, which I believe is very important, is the system manager in MOE. So at the very top right of the MOE window, you'll see this blue button called System. And when you click on it, this panel opens up. I highly recommend you attach this panel, this application, to your MOE window. And you can do that by clicking on this downward arrow right here. So if you click on it, it will attach itself to the MOE window. Now, the system manager is quite important because what happens is that right now, I only have a single system loaded up in MOE, and it'll become evident progressively why the system manager is very useful. It allows you to control everything that is visually displayed within your 3D environment. So right now, the system that I'm displaying is 1M17. That's here. This is the parent. If I click on this, everything will be hidden. All right, both the ligand, solvent, receptor. See, I can hide and show. Everything beneath it are its components. So there's the receptor, the solvent, and the ligand. The top 1M17, the parent, this in MOE is referred to as a tag. And everything below the tag, so the children of the parent, are called chains. So you have the receptor chain, the solvent chain, and the ligand chain. You can hide and show the ligand, the solvent, as well as the receptor. Now, the system manager has a number of different buttons. So if we focus on the vertical columns, this middle column, you know what it does. It's essentially hides and shows, right? Then you have this column called the A column. This is the state of your particular component within the MOE environment. Right now, all the components are in the active state. That means that when you run a calculation, they will participate in that calculation. If I have this turned off, or if I click on it, an eye will appear. That means that that particular component is in its inert state. Even though the structure is displayed within the MOE environment, MOE will disregard the receptor in the calculation because it's inert right now. So the active state is independent of display. I can have it active, but hidden. So even though you don't see the receptor, it's active. MOE recognizes it, and it will participate in the calculation. So that's what this A means. This column over here, the buttons where you see these circles, these allow you to select the atoms of that particular component. So right now, I've selected all the atoms of my receptor. So you can select them and then move into the right-hand sidebar and say show selected, and it will show you all the selected atoms of the protein. So this is a selection button. On the right-hand side, where you see these colored squares, these allow you to change the receptor color. So for example, if you want to change the color of the receptor green, and then maybe bring back the ribbons of the receptor, Let's color the ribbons green as well. These buttons allow you to modify the rendering of the ribbon color and atoms, the bonds, and the ribbon right here. The S over here is allows you to generate surfaces. So it's a shortcut to another application that allows you to generate surfaces in MOE. We'll get to this shortly. And I think the X is quite evident. It's the delete button. So if you want to delete the receptor, MOE prompts you and says, are you sure you want to delete all 5,000 atoms of this receptor? We're not going to do that right now. We're going to cancel it. But that's what this X here is. All right. Now that we've got the protein prepared, we understand what the system manager does. Let's get into it and let's evaluate the active site. Well, when you have a protein like this, well, you need to know where the ligand is. Well, I can select the ligand, and that will highlight, for example, the ligand. But this is not a very efficient way of visualizing. One way of visualizing the active site that's very efficient is to actually click on Site View. What Site View will do is it will identify all the ligands that are within the MOE environment. So in this particular case, we only have a single ligand. So it's going to focus on the ligand. It's going to generate a sphere with a radius of 4.5 angstroms from the ligand atoms. And then it's going to display everything within that sphere. So if I click on Site View, notice what happens. The rest of my protein is hidden. There's a sphere. I think it's a bit more than 4.5 angstroms because I think I had changed my settings earlier. Just give me 1 second here. Yes, 4. We'll put that apply. Sorry about this. This is what happens when you play with your settings too much. We'll click on Site View. All right. So now when you click on Site View, what it did was it generated a sphere with a radius of 4.5 angstroms from the ligand atoms, displayed all the atoms and ribbons that are within the volume of the sphere, and hid all the ones that are beyond the sphere boundary. All right. So that's what we see over here. So if we look at the ligand right now, we can see that it's picking up at least 3 different interactions. All right, so we've got with this quinazoline scaffold, there are 3 hydrogen bonding interactions where the quinazoline scaffold is participating with 2, and then there's this bridging interaction with threonine right here. I just want to remove the ribbon to remove some of the clutter for it to be displayed much more clearly. All right, so that's how you do it. You just go to the receptor, click on no ribbon, and that will hide the ribbon. So we're looking at the interactions between the quinazoline and the receptor. What would be useful right now is for all the residues that are around or maybe even interacting, it would be good to have labels. Now, there are multiple ways of labeling things. In MOE, what you can do is if you want to see all the residues that are displayed, you would simply go to Atoms and then click on Residue, and this will display all the residue names of that are visible. All right, so you can see methionine, leucine, and so forth. Now, let's say, for example, you don't want to do that, but you want to do a select number of residues. If I just go back to residues and click on it, it's a 2-way toggle, these buttons, so we can hide it. And then if I return, and if I select an atom of a particular residue, let's say that one, this atom on the oxygen, and this hydroxyl group, and I'll go to Atoms Residue. I can display only the labels of the residues next to the atoms that are selected. All right, so there you go. These are the key residues that have been selected right now. Threonine, glutamine, methionine that are participating in the interaction. Now, if you look closely, you'll notice that some of these interactions have this very thick cylinder bond, and some of them have small ones, some of them are just dashed. Now, there's a qualitative element to this in terms of the overall interaction strength. The thicker the cylinder, the stronger the interaction, the less thick, the weaker the interaction. So this non-standard interaction with glutamine 767, well, that is a weak interaction with glutamine 767, all right? So this is a straightforward way of visualizing the hydrogen bonding interactions, arene type of interactions. If you had a hydrogen arene interaction present, you would be able to visualize it. Right now, in this given example, we don't have that, but if it was present, you would be able to visualize it. Now, this is a quite simple system, and visualizing the hydrogen bonding or polar interactions are quite easy. There's just these three interactions. But sometimes when you might have, let's say, a macrocycle or a peptide, you'll have many more interactions, and visualizing within a 3D environment makes it actually quite difficult. So what you can do in those cases is use the 2D ligand interactions. So from the right-hand side menu bar, if we go to ligand interactions, this panel opens up, and I'll just expand it. And this is a 2D view of the 3D space that is visible within the MOE environment. So what we do is we'll flatten out the 3D space. So all the residues are displayed in these beads. So that's what they look like. The hydrophobic structures are in green. The hydrophobic residues are in green. The polar residues are in pink. The ones that have a blue circle, the pink residues that have a blue circle, those are positively charged. The red circle are negatively charged. You also notice that you have these blue gradients around the ligand atoms. What that means is that that portion or those fragments on your ligand are exposed to bulk solvent. So these polyether chains are exposed to bulk solvent. You also pick up the interactions. So the interactions are indicated by these dotted lines, and the way the arrow is pointing, the direction of the arrow points towards the atom that has the lone pairs. So for example, the nitrogen has the lone pairs, that means the hydrogen is on the methionine that's participating on the nitrogen. So it has directionality in terms of the interaction. Now, you also notice that some of these residues have this blue crescent around them. Some of them are very pronounced with a deep blue color, some of them less so, like, for example, this glycine 772 versus the leucine 694. What that means is that in the absence of the ligand, this leucine is very exposed to solvent, all right? And in the presence of the ligand, this leucine is actually shielded from bulk solvent. So it doesn't have access to solvent anymore, or solvent exposure. That's what this crescent means. So the larger, deeper color means greater exposure in the absence of the ligand, and not so much in the presence of the ligand, all right? So this is a 2D interaction map. And then you also have this dotted contour that gives you an idea of the overall steric space of the ligand. So you can see that in this region of the phenyl group, you probably have some space to further elaborate, maybe put a methyl or chloro substituent, but not so much in this region right here, or around the nitrogen. You wouldn't be able to kind of put a substituent off of this position because you might be clashing. For those of you who are interested in generating and then capturing these images, you could easily do that by clicking Copy EMF or clicking on the Export button and then selecting the format, the picture format, and then you can take this, put it in your report, PowerPoint, publication, whatever type of documentation that you're using to paste it in there. All right, so now we've seen two ways of visualizing interactions. So there's the 3D visualization space, the 2D ligand interactions. But in both of those cases, we're only able to visualize hydrogen bonding interactions. And now I also want to mention that the hydrogen bonding interactions that we're visualizing, there's actually a cutoff. That cutoff is 0.5 kcals. And you can modify that cutoff if you click on the contacts button right here, and then modify this value. So this is the 0.5 kcal. You can see that if I increase the value of my cutoff, eventually you will find the interactions, some of those interactions will disappear. So right now, those interactions, both the bridging water and the non-standard interaction with glutamine 767 was less than 2.3 kcals. The methionine 769 is much greater than that, all right? So let me just revert this back to 0.5 and let's display those interactions. Now, those are all hydrogen bonding interactions. We're not taking into consideration the hydrophobic interactions. If I look at this, for example, this phenylacetylene fragment, the polyether chains, the quinazoline phenyl group, those are, lipophilic, they're hydrophobic in nature. And so they're participating because they're occupying the space. That means that the environment around them must be hydrophobic as well. And so the question is, how do we get, data in terms of which residues are participating and what is the overall interaction energy, and so forth. Now, to be able to do that, there's an application in MOE under protein contacts. And then when you open that up, this is the application. This application is divided in 3 sections. You've got the top section where you set up your query. The middle section, this is where the output will be generated. So you'll get a table. And then at the bottom, you have a number of filter options. So let's set up our query. We want to display the interaction between the receptor. So set A will be a receptor. So I'll just leave that as such. And then set B, we're going to call this our ligand. All right, so there's the ligand. And then once I've set up my query, I'll just leave the default settings, click on search, and now it will run the calculation and it will output the list. So right now it output 2 hydrogen bonding interactions. Remember, set A is my receptor, so it's represented by the chain A, position A, set A. It lists the residues that are participating in the interactions, and this is my set B. AQ4999, that's the label the depositors of the PDB file gave the ligand, Tarceva. All right, so this represents the ligand. It shows you the energy of the interaction between the ligand and the residue. So in this case, between glutamine 767 and the ligand is 0.6 kcals, the distance of that interaction, and then the overall area, the interacting area, the contacting area in square angstroms. So you can see that it's quite large. It's about 6 square angstroms right now. And by the way, this table is sortable. So if I click on it, you can sort it in ascending or descending order. Now you'll notice that when I generated this interaction, it only listed 2 hydrogen bond interactions. But if I look at my 3D visualization space, my quinazoline scaffold actually has 3 different interactions, right? Yes, Suha, you have a question?
Yeah, my question pertained to the 2D interaction diagrams that you showed earlier. So
Yes.
I was wondering if we have like protein ligand complexes from some other software. For example, my lab uses a lot of Yesara for docking. So
Yes.
if we use some other complexes and say save it as a PDB, will MOE recognize the interactions that are taking place, and can we use the figures from these ligand interactions?
Yes. Yes, you can.
Perfect.
So what you need to do, you have to ensure, because once you generate, so once you open up your ligand interactions, your ligand interactions, this portion of it, you see this section right here where you see a receptor and ligand? This is where you set up your query. By default, MOE selects the receptor to be a receptor plus solvent, and it identifies the ligands, all right? In this particular case, we only have a single ligand. But in some cases, you might have multiple ligands bound in different parts of your protein. So it will actually identify all the ligands, and then you'll have up and down arrows right here. So you can visualize the different pockets that the ligands are bound in. But you need to ensure that your ligand is defined as ligand atoms or give it a definition. I'm going to come to it in a second. But this is what you need to do. You can even visualize residues and what's surrounding that particular residue. I'll give you an example. So let's say, for example, this threonine is of interest. All right, so I'll select the threonine. and I'll go to my ligand interactions. So what I want to do is I want to look at the receptor, but instead of the ligand, I'm going to say selected atoms, because I selected the atoms of my residue, and click apply. This will show you all the residues around your selected residue. So this is where you're setting up your query, right? What is the environment? That is the receptor. And what are you trying to interrogate? That's the ligand. And so you can see over here that if I make this a bit bigger, glutamine is attached to my threonine, which is attached to leucine. So it's covalently bound. And these are the interactions that are taking place around this residue. So you can look at it between ligand, cofactor, and receptor, DNA, RNA, protein, any combination you can think of, you can use the ligand interactions map to do it. Does that answer your question, Sua?
Yes, thank you so much.
Yeah, all right. So now, coming back to the protein contacts, you see over here that there are two interactions, but in my 3D, my quinazoline has three interactions with the complex. But you have to be careful because this third interaction is actually with a bridging water. And what we set up as the query, we said set A had to be receptor. So MOE will remember, the modeling environment is very explicit. What you tell MOE to do, that is exactly what MOE is going to do. I told MOE to take all the receptor atoms and calculate the interactions with the ligand. And that's what it did. I didn't tell it to include the solvent atoms. If you want to include the solvent atoms, or maybe you might have a cofactor, like let's say ATP, that is adjacently bound, that might be interacting with your ligand, or you might have some other fragment that's interacting your ligand. What you need to do is change the definition of your receptor to include that fragment or fragments, all right? And so that's what we need to do. Now, that's very simple to do in MOE. The way we do this is through the system manager. We'll go into the system manager and we'll select the receptor component, the solvent component. So once you've selected what you want to define as your complete receptor definition, you'll go to select and then set create. And this will swap the header menu for a prompter. This is the set create prompter. And you'll give it a name. You'll call this my protein and solvent. All right. So something descriptive so you can remember what the collection of atoms that you've selected are describing. Okay. And then once you write that, press enter. And what that does is in the system manager, you'll have a new line item called sets. Right now I have 3 sets because during structure preparation, I created this set, but a third set that I created was right now. This is my protein and solvent set. All right. So if I deselect, I can select those 2 components using this option right here. Okay. Now what I can do is I can go back into my protein contacts and I can say set my protein and solvent. There's a real-time monitor in MOE applications that every time you create a set, those menus will get updated with your set, and I'll select it. Now what I want to do is I want to evaluate my new definition of the protein with my ligand. And if I click on search right now, it will recalculate, and notice what it did. Oops. It actually has 3 line items right now, right? Because it includes the water inside there. Okay. So so in all cases, you'll notice that the type of interaction that I'm displaying are hydrogen. The H's right here mean hydrogen. The type of interactions that you can visualize in this application are indicated below the window right down here. You can evaluate hydrogen bonds, metal interactions, ionic interactions, arene, if you've got covalent interactions. And by default, you'll notice that distance is disabled. Distance is a surrogate for van der Waals types of interactions. So those are a surrogate for hydrophobic types of interactions. You can enable it, by default, it's disabled. If I turn this on, notice what happens. A whole bunch of interactions open up. So let's sort this by energy, and let's look at some of these interactions. So this is the strongest interaction that exists right now in this system. So if I select it, notice what happens. Some colored contours appear within the MOE environment. So there's my cysteine. I believe it's, yeah, is it cysteine or methionine? It's a methionine, sorry. So there's my methionine, and there's the interaction that my methionine is having. So the colored contours represent the atoms that are participating in that interaction. Now, if we move to the next one, you'll notice that this one here has D as the type. So this is the van der Waals types of interaction. So this is a hydrophobic interaction. It's taking place with leucine and my ligand, and it's almost 4 kcals. So let's take a look at that interaction. If I rotate my structure, you'll notice that it's right above the plane of my quinazoline scaffold, right? So this is where my leucine is. So let's take that leucine, let's label it. So that's leucine 820, and it's right above the quinazoline scaffold. Now, if I look at the third strongest interaction, that's about 2.2 kcals. That's on this side down here, and that happens to be another leucine. All right, so there, let's label that one too. So I've got 2 leucines, and my quinazoline scaffold is essentially sandwiched right in between those 2 strong hydrophobic residues. So it's not only the polar interactions that are very relevant, but in terms of binding affinity, but the hydrophobic interactions are also very important. All right. So I've shown you 3 different ways in terms of how you can evaluate interactions. You can visualize the interactions in 3D, the 2D interaction maps, and the protein contacts. The protein contacts, it's nice because what it does is that you can also visualize those hydrophobic interactions, and it shows you the atoms that are contributing or participating in that hydrophobic interaction. Notice the rest of the leucine atoms are not participating, right? It's only the distal, the beta gamma type of carbons on the leucine that are participating, at least for this one and this one right down here. Now, this is very important in terms of visualization and understanding which residues are contributing what type of interactions and the properties that they impart. But whenever we're looking at structures, what's also very important is the topology, because this ligand has a certain conformation. If my ligand conformed in a different way, it might not fit. So the topology of the active site is also very important, right? I mean, the way the side chain conforms affects not only the hydrophobic nature, but it also attributes to the overall form of the active site. Now, to evaluate and look at the topology of the active site, we'll have to generate surfaces. So in MOE, yeah, there is a question, Zico?
Yes, my question is, in terms of visualization for the hydrophobic interaction, is it possible to differentiate them in terms of colors? Since we had 2 important hydrophobic interactions, they were all in pink, can we make one of them blue and say the other one pink?
Yeah, so you cannot, change the color of the contours. You cannot change the colors of the contours in the panel right here. But what you can do is you can select the atoms and color them using the surfaces, because then what you'll do is you'll inherit the color of the residues. So by coloring the residues, you can map those onto the surface. I'll show you how to do that since I'm gonna do it right now. All right. So let's do it. Let me change the color back of my protein, because right now all my carbon atoms are green, but I'm going to change that to gray. All right. And then coming to your answer, I'm going to take this leucine residue and I'm going to change the color of this leucine residue to, let's say, green. All right, so I'll call this green. All right, so you can see that the atoms are green right now. And then for the other leucine, which was down here, I'll select this one and I'll change that a different color. I'll make that a deeper green. Okay. You have, by the way, a large selection of colors by clicking on this color palette and then selecting a large number of colors. All right. There's a whole gradient you can do. But you'll notice that both of my leucines have changed colors right now. Okay. Now what I want to do is I want to generate a surface around this. So I'll go to Surface, Surfaces and Maps. And in Surfaces and Maps, this is the panel that allows you to generate surfaces around your protein or parts of your protein. At the top, this is the window where all your surfaces will be listed. We'll give our surface name a name. So we'll call this molecular surface. Molecular surface, all right, some descriptive name. The type of surface that we want to generate right now is called a molecular surface. There's a number of different surface types that we can generate, but today I'm just going to focus on molecular surface. We're going to generate the surface around the receptor atoms, but only near the ligand atoms. I don't want to generate it around the whole protein, all right? So I just want to generate the surface near the ligand atoms up to 4.5 angstroms away. And the type of surface that I want to generate is atom color. So I want to inherit it from the atom colors, all right? And then we'll click on Create. And what this is going to do is it will generate a surface, and there you go. Do you see the surface right here? It actually inherited from the atom colors that are in proximity. For this one, so the leucine is here, and the other leucine is in this region. Does that answer your question?
Yes, it does. Thank you.
Okay. So you can really play around with this. Now, all the rest of the colors that you see in this region where you see gray and blue and red, those are inheriting the colors of the atoms that are in proximity, all right? So the oxygen is here, it's red. These cyans are the lone pairs. That's the direction of the lone pairs that they're pointing. The blue is the nitrogen, all right? So there's a nitrogen in proximity right here. And then if we look very closely on this side where you see yellow, there's a methionine, there's a sulfur, and it's lone pair. Okay, so you can color it by atom type, and then you can change the color of the surface. Now, there's many other ways of coloring. So, for example, you can look at lipophilicity. What that does is that it will color the lipophilic regions green, hydrophilic regions purple. And if we look at our fragment, you'll notice that this region right here has a very large hydrophobic or lipophilic region. And on the other side, where you see this leucine, that also is quite lipophilic in that region as well. So this is one way of evaluating the different properties of the surface, as well as looking at the overall topology. You'll notice that the barrier of my protein ends here. This is where the phenylacetylene is situated, right? Beyond the phenylacetylene, there's no more room. That's the barrier of that's the protein wall. I can't go beyond that, okay? Now, there are other types I can evaluate by electrostatics. So the blue regions are partially positive charge, negative regions are partially negative charge, white areas are neutral. And you can see that the neutral area over here is hydrophobic. And then previously, where you had purple, now we can break the purple areas down into partial negative and partial positive charged areas. Now, when we're looking at these types of surfaces, we're mapping the property onto the surface. But in reality, this active site is actually a volume, right? This ligand is occupying a property volume. For example, if I just hide my surface right here and I look at my ligand, the quinazoline scaffold, when it fits in a region, it's occupying a certain property. There might be, for example, partial negative charges here, or maybe where the water molecule is occupying, where the oxygen, in fact, or this phenylacetylene is occupying a volume that is hydrophobic. Now, although we've mapped it onto the surface, it would be nice to visualize those volumes, those property volumes within the active site. One way we can generate volumetric properties is, instead of using molecular surface, using electrostatic map. And I'll just change the hydrophobic for green just for to make it more pronounced. And instead of mesh view, we'll look at it solid view. So right now what I'm going to do is I'm going to generate a volumetric map. So we'll call this vol electrostatic. Okay. And then we'll click on create. So again, I'm going to generate this volumetric map around the receptor atom, but only near the ligand atoms up to 4.5 angstroms away. And then let me just hide this. Okay. So now what we did was we generated a number of these volumes, all right? The blue regions are donor regions. So those are partially positively charged regions. The red regions are partially negative charge regions, and the green regions are hydrophobic, all right? And there's a certain cutoff. Right now, these sliders allow me to only visualize hydrophobic regions that are 3 kcals or above, all right, not below. And the partial negative and positive regions are above 2 kcals. So let me hide, and let's go through this systematically one at a time. So when we're generating these volumes, this is what the receptor properties are like in the absence of the ligand, all right? So if the ligand wasn't there, this region right here, this volume is hydrophobic in the pocket of the receptor. Now, if I put the ligand back in, you'll notice that Tarceva occupies that volume quite nicely. And in fact, it even shows the linearity of it, all right, of that hydrophobic volume is nicely covered by the phenylacetylene fragment. So it's very compatible in terms of the volume that it's occupying. The same thing can be told about this carbon ring junction. Now you'll notice that there's a hydrophobic region right here that's not being exploited. So that's probably, something that we can consider when we're designing our ligand, when we modify our ligand, all right? Now I can do this analysis with all the other properties, for example, the acceptor. So these are partial negatively charged regions. So if we look at this, you'll notice that the nitrogen lone pairs are nicely overlapping in that region. The oxygen lone pairs are nicely overlapping this region of this bridging water, all right? And then if I look at the donors, so those are hydrogen bond donors or partially positive charge regions, you'll notice that the hydrogens of the water, as well as this non-standard hydrogen, which is in between the amidine fragment or pyrimidine fragment, nicely overlaps this region as well, all right? Now, if we look at the vast majority of these blue regions, Tarceva doesn't satisfy it. So there's a lot of different opportunities for us to maybe further optimize Tarceva to see if we can go out there and grab one of these volumes. And that's what I'm going to be discussing right now. So through our topological analysis, or using the surfaces and maps and the interactions, we can generate a hypothesis, right? We can say, all right, the topology of Tarceva is very good because, we need a flat molecule to fit in between the leucines. The water is playing a role. It's nicely interconnected. So displacing the water with a substituent might be very difficult because the water over here has a dual role, right? It has a donor acceptor. There's almost a push-pull type of interaction that's going on right here. And finding a substituent to replace that water would be very difficult. So we could leave that as a water as an interaction feature. And then when we're looking at these donors, we can say, all right, well, Tarceva is not satisfying because there's no overlapping regions right here. How can we modify this ligand to kind of go out there and capture one of these blue volumes? Now, in the literature, there is a compound that is this compound right here that has this type of butanoic derivative right here. All right. So what we're going to do in this example is this also interacts with EGFR, but not to the same IC50 level as Tarceva does. But nevertheless, what we're going to do is we're going to take this fragment and we're going to graft it onto Tarceva. So we're going to delete the polyether chains and graft this aminobutanoic derivative right here, or this aminobutanamide derivative onto the quinazoline scaffold to see if this charged amine can interact with the residue such that it overlaps in one of these regions. Now, in the MOE environment, you can actually run those what-if scenarios because it's essentially running an interactive simulation in the MOE environment. Now, to be able to do this, we'll need a reference point. Our reference point is Tarceva. So we would, before modifying your ligand, it would be nice to calculate some of the properties, see what the affinity, the overall strain is of that particular ligand. And that can be accomplished going through ligand and then turning on properties. And when you click on that, you'll see a number of descriptors will appear at the top right. So you'll see molecular weight, topological surface area, log P, log D. I've customized mine. I've included a Payne's filter in there. Right now, Tarceva doesn't meet the Payne's filter, right? So that's good. That means that it passes the Payne's filter. So this is a descriptor. And now if I click on minimize, what this will do is it will also display a strain. So this ligand in its bound state has up to 5.79 kcals in strain, and the affinity against EGFR for Tarceva is minus 8.22 kcals. Okay, so this is my reference starting point. You can jot these down, you could snap a photo of it or something, but this would be your reference. Now, to begin modifying your ligand, what's important is you can modify the ligand as is, but I would recommend duplicating not only the ligand, but duplicating the whole system. To duplicate something within the MOE environment, all you need to do is just go on the chain, right-click, and then this pop-up appears, and you can click on duplicate. And when you duplicate it, it will hide the original, and it will only display the copy, all right? But right now, if I modify my ligand, and then I click on minimize, I'm also going to slightly perturb the side chains of my receptor, and I don't want to do that. What I want to do is I want to keep a reference structure, the reference complex, and then modify the whole complex so I can see if there's any side chain perturbations that are taking place as well. In MOE, if you do a mistake, it's not a problem. Just go to Edit, Undo, or press Control Z, and it will undo it for you, all right? So you can see that I undid my duplication of my ligand. Instead, I'm gonna duplicate the whole complex. So right-click on the tag, and I'll click on Duplicate. All right, there you go. This is the original complex, and now I've got a duplicate copy right here. I'm going to deselect, and I'm going to start modifying my ligand. Now, to modify your ligand, you can simply just select the atoms and click on delete. But in order to be able to delete and then build, you'll need a builder. So if you click on the builder button right here, it will add the builder within the MOE environment. Usually the first time that you open up the builder, it will be a floating panel. You can click the attach button to attach it. So you've got a nice environment right now where you can modify your ligands using the builder, manage your system on the right-hand side, and apply the selections in the middle. The builder has multiple modes. So this is the molecular builder. There's the protein builder. So this allows you to modify residues, sequences, peptides, and so forth. There's the DNA RNA builder. And then there's the carbohydrate builder. So this is a bit beyond the scope of today's talk. I'm just going to be focusing on the molecular builder right now. So once you've selected, so what I did was I clicked and I dragged a box around my MOE atoms that I want to delete. But notice what happened when I clicked and dragged the box. I also selected my protein residues. I certainly don't want to delete those. So in MOE, to prevent the selection of non-ligand atoms, what can be done is a mask can be applied. At the bottom, right above the soccer ball, right next to it, there's this thing called RSL. If you click on it, it'll turn red. This is a mask. R stands for receptor, S is solvent, L is ligand, and the thick arrow are ribbons. So you can prevent selecting ribbons as well. So right now, if I go back into my MOE environment, notice I can't select my receptor atoms anymore because there's a mask that I have applied. I'm going to apply the mask both on the receptor and the solvent. And now what I'll do is I'll select the polyether chains and I'll delete it. Now in MOE, there's actually a feature called R vectors. And in R, what that does is that it will kind of automatically show you where you can grow your ligand, where in the sense that it will show you whether or not you have enough steric space to modify your ligand. To turn on the R vector option, you'll need to click on ligand R vectors. And the minute I do that, you'll notice that these green arrows will appear on your ligand. All right, you can see that there's some on here as well. This is showing you that at the very least, you can introduce something like a substituent the size of a methyl group or a chlorine without introducing any clashing interactions. What I want to do here is I want to introduce and elaborate my ligand on over here, but I have two vectors. I can elaborate it here, or I could elaborate it here, okay? Both are plausible. I mean, if I grow my ligand here, I can target these volumes. If I grow it here, I can target this volume. I'm going to select this one. Why? Well, the reason is because in my molecule from the literature, this is the position that they've used. And this quinoline is a surrogate for my quinazoline. So these nitrogens are identical and they interact with the same hinge binding residue. So I'm just going to keep with the literature and go with it. But in your case, let's say you were on a design project, all you would need to do is just click on the system manager and duplicate a third one. And then for the third one, for the third duplicate, what you would do is you would use this vector to elaborate. And for copy number 2, you would use this position to elaborate. And you can then compare and see how both of those would interact, both in terms of properties, affinity, strain, and so forth. Okay, so this environment is really to run your simulations in an interactive way and try to figure out. So it's really about ideation, coming up with ideas, and testing out your hypotheses. Okay, but today I'm just going to focus on this region and I'm going to build it. So the first step is we'll select the atom, we'll go to the builder. You have a number of templates. Instead of building one atom at a time, I can select the functional group template, and that will install it for me. Now, when it installs the functional group, it doesn't do it randomly. It takes into consideration the environment around. So it optimizes the torsions about the bonds. How do I know this? Well, if I select the bond, some options will appear at the footer. I'll do it again. Notice there's nothing at the footer of the MOE window right here. When I select the bond by clicking on the bond, a few options appear. It tells me the distance between the atoms, so the bond length. And then to the far right, there's this plot icon. If I click on that, the dihedral plot will appear. you have two curves right here. You have a solid curve and you have a dotted curve. The solid curve is the torsion about that bond in the presence of the receptor, and the dotted line is in the absence of the receptor. Notice that the torsion in the absence of the receptor, this is what it would appear like. And it's interactive. When you click on it, your torsion will move. All right, you see that it kind of moved right here. I can revert back to its original state by just undoing it. All right, so if I just do undo, it'll revert back. So MOE placed it in the minimum. It didn't randomly place it, and it didn't place it in this low minima either. It placed it in the lowest state it could. So that's how, and it does this for both torsions, this one as well as this one right here. So if I go click on that one, you'll notice that there's a single low energy state right there. All right, let's continue. But before we continue, let's see where we are in terms of affinity. So once you've elaborated a little bit, you'll click on the minimize button here or in the builder. And this will run the minimization. And now what it's going to do is it's going to output the strain and the affinity. And in addition, as you're elaborating your ligand, notice that your descriptors will automatically get updated in real time. All right, so these are changing all in real time. Notice my strain went from above 5 kcals to roughly less than 2 kcals. And that's not surprising. I have less number of rotatable bonds, so there's not much strain in the system right now. But of course, that also affected my overall affinity. I almost lost a kcal in terms of affinity. I went from minus 8.2 to minus 7.2. So this is, in terms of affinity, less, it has less affinity against Tarceva than Tarceva itself. All right, so let's elaborate a little bit more. Let's select this hydrogen, and then we have to add 3 more carbons. So 1, 2, 3, and then we'll add a nitrogen. And then we have to protonate that nitrogen because it's exposed to solvent and at a physiological pH, a primary amine is protonated. So we'll protonate the system, and then we'll click on the minimize button. Now, when I'm minimizing, you'll notice that already this nitrogen is in proximity and overlapping this volume right here. You can see that that hydrogen is really overlapping that volume. And what we need to do is we need to reset our site view. Remember, when we initially clicked site view, it used Tarceva as the reference molecule. So it used all the Tarceva atoms, generated a sphere 4.5 angstroms away from those atoms, and then displayed everything within the sphere. But right now, this molecule chain is much longer than the polyether chains, so we need to reset our view. So if I click on site view, you'll notice that a new residue will appear that was previously hidden, and now it's interacting with my amine. You'll notice that the strain has gone back up to about 5 kcals, and my affinity is minus 7.82. So it's not as good as Tarceva, but it's in the same range. So within the modeling environment, 0.5 kcals, it's not huge. You're not going to be able to distinguish between, a good binder or a bad binder with only 5 kcals. In this particular case, it's actually less than 0.4 kcals. What you're looking for is usually to have some significant signal. You're looking for anything, above 1.5 to 2 kcals to say, all right, maybe if there's a difference of 2 kcals, then you can probably make the assertion that, okay, there might be a significant binding difference. Yes, Veta, you have a question?
Yeah, what are the numbers in the brackets, the parentheses?
Yeah, so those are the strain energy in kcals and the errors associated with it.
How are those errors calculated?
Yeah, I would have to, I will point to it later. I will email it to you and I will describe that to you.
Yeah, okay.
I don't have it off the top of my head. I can't tell you right now. I'm sorry.
That's all right. Thank you.
Yeah. Okay. So right now, yeah. So strain affinity. Okay. So now what happens is that, remember that this is only a single solution that we're generating. And when you look at this side chain, right, this side chain is quite floppy. There is it's in all likelihood, this chain, given the fact that it's open to bulk water, it's actually going to have multiple different conformational states. It's very dynamic. It's not going to, be glued to this aspartate. And so the question is, what is the frequency of this side chain interacting? And is this interaction strength strong enough to have it interacting with the aspartate, let's say 90% of the time or 80% of the time? So those are all questions that need to be answered. And of course, further simulations need to be run in order to make that assessment. One way of making that assessment is really to do some conformational searching and trying to find, which conformational state are favorable conformational states pointing towards the aspartate or some other regions within the space. And the way that can be accomplished is through compute conformation search. That allows you to run conformational search in the presence of the receptor. Again, that's a bit beyond the scope of today's session. But all this to say that all these things are possible. Other methods that one would use to evaluate would be to do compute simulation dynamics. So you would set up a molecular dynamics run to see the overall stability of this ligand against the receptor and collect all the trajectories, evaluate the conformations of those trajectories, see whether or not this interaction is retained throughout your simulation. Today, what we're going to do is we're going to hit two birds with one stone, and we're going to take this molecule, we're going to dock it using Tarceva, and we're going to run conformational searching at the same time. All right. Now, to be able to do that, I will need to redefine, or I need to distinguish the ligands from each other. That means our modified ligand from Tarceva. And I'll explain to you what it is shortly. All right. Now, to run docking in MOE, it's quite straightforward. We'll go to compute, dock, and that will open up the docking application. All right. So this is the docking application in MOE. On the left-hand side, there are a number of different scenarios. So you can run general docking, template-based docking, electron density. If you have covalent inhibitors, you can use covalent reactions to covalently bind your structures. You can use protein-protein docking. Pretty much any type of guest-host interaction you can think of, this docking application will be able to run it for you. All right. So it doesn't matter if it's RNA, DNA, protein, peptide protein, any guest host interaction, this application will be able to run it. Today, what we're going to do is we're going to run template-based docking. Why? Well, the reason for why we're going to be running template-based docking, it's because our structure, Tarceva, has the quinazoline scaffold. It's already crystallized within the active site. And our modified ligand, we just added this chain. So what we're going to do is we're going to use the quinazoline scaffold of Tarceva to guide the docking of this ligand, this modified ligand that we generated. And we're going to run conformational searching on the fly. Now, to run docking in MOE, it's pretty straightforward. At the very least, you need three items to define. The first one is the receptor. Where is the receptor? Right now, it's in our MOE environment. It's in right here in our 3D visualization space. So we're going to leave this as use MOE system. We're not going to say anything because it's not in a database. It's not in a file. It's present in our MOE system. The next thing we need to do is define our receptor, give it a definition. Just like we did for the protein contacts, what is your receptor? What does your receptor consist of? Are you just, for example, do you just want to consider the receptor atoms? You want to consider the receptor and the solvent atoms. You want to consider the receptor as your protein and your cofactor. You got to give it a definition, and you can do that by creating sets. We did that earlier, and you can, once you've created that definition in terms of sets, you can select that set over here, and that's the collection of atoms that are going to be used as your receptor. The next thing that we need to define is the site. So where is the site? Now, given the fact that in our previous structure, we had Tarceva, and let me just color this orange for so Tarceva is colored in orange. You can see that this is where Tarceva is. Given the fact that it was already co-crystallized there, what we're going to do is we're going to use Tarceva to guide our docking. It's going to be describing the volume that we're going to be using to dock our ligand. Now, the issue right now is that I can't say the site are my ligand atoms because I have two active ligands in my system. I have Tarceva, right? So I have this ligand right here, which is Tarceva, and I have this modified ligand that I created, right, with the aliphatic amine. So what I need to do is I need to distinguish them because I want to define the site using Tarceva. To do that, we'll select Tarceva. So just the Tarceva atoms are selected. And then we'll create a set out of that. We'll say Tarceva. All right, so there it is. We created a set. And the next thing I'm going to do is I'm going to go to my modified ligand, and I'm going to call this, I'm going to give it a name, set create, and we'll call this inhibitor. XXXX. We'll give it some number. All right, so this is my ID. All right, so there's my set for the inhibitor. Just make sure that you are selecting the correct ligands, the right number or the right collection of atoms, or so your selection is correct, because otherwise your definitions of your sets are going to be incorrect, and that will have consequences when you run docking. All right, now that we've created our sets, we'll go back to the docking application. And now we'll say the site is defined by Tarceva. And the next thing that we want to do is define our ligand. My ligand right now is in the MOE system. And you can see MOE identifies two ligands in there. It identifies Tarceva, and the other ligand, it's this one right here that I have modified. Yes, Suha, you have a question?
Yeah, I was just wondering if we can use the inert feature to still define the ligand site. Earlier, you mentioned that we can make certain parts of the protein inert so that it is not included in the calculation. So
Correct.
Instead of creating a different set, can we make that molecule, which was the co-crystallized structure ligand, in the protein inert, and then use the same option under site and use the second modified one as the ligand for docking, or no?
Yes, yeah, you absolutely, you can. You can just make this inert. See, look, I just want to show it to you. Right now, you see ligand 2 of 2, right? And you see Tarceva right here. If I go into my system manager and I turn and make it inert, if I go back to my docking, it's ligand 1 of 1, Tarceva is no longer present, okay? The reason why I chose to do it with Tarceva and not make it inert, it's because sometimes, imagine, for example, that I had modified my ligand, and my ligand had kind of slightly moved away from the, let's say, the quinazoline scaffold coordinates had kind of slightly moved away, or it had moved away a lot. Then what happens is that it's not occupying the same site as Tarceva. And so I want to ensure that it runs using the correct crystal ligand definition of the site volume. And that's why I chose to use Tarceva. So I'm going a step further to show you that you can actually distinguish ligands within MOE by creating sets, and defining the different elements or parameters within your docking panel using those sets. But yes, absolutely, you can make it inert. And if you choose to use the ligand, and if your modified ligand occupies the same space as the site you want to dock, absolutely, you can do it by just using the inert. Does that answer your question?
Perfect. Thank you so much for the clarification. I appreciate it. Thank you.
Yeah, you're welcome. All right, so that's okay. So receptor we've defined, site we've defined, ligand I'm going to define right now by selecting inhibitor XXX. All right, so my ligand is in MO, but the ligand that I'm interested in docking is this one right now. And you can see MO updated it, said ligand 1 of 1, Tarceva is no longer there. Now, what I want to do next is I want to guide the docking using Tarceva. And in Tarceva, I've got this quinazoline scaffold, so I want to use that quinazoline scaffold, but using Tarceva. So if I click on 2D right here, because it's going to be very difficult for me to select the Tarceva atoms of the atoms of the quinazoline scaffold of Tarceva versus the other ones, because they're on top of each other. But one way I can select them is to actually click on this 2D button right here. What that will do is open up a 2D depiction within the MO environment. And this is selectable. And you can browse all the ligands that are within the MO environment. Right now, there's 2 that's active, right? So if I click on these arrows. So if I display Tarceva, I can just go and select the Tarceva atoms from the 2D depiction, and only the Tarceva atoms will be selected. All right, so that's one way that kind of facilitates the selection process. Now that I've selected it, I can go back to my docking application, and under template, I'm going to select substructure because I'm going to use a substructure to guide the docking. The template comes from Tarceva. All right, so we'll mention Tarceva, and it's the selected atoms of Tarceva. That's the query. If I have a matching scaffold on my ligand that I'm interested in docking, it will get highlighted. And you can see that it got highlighted, the fragment that I'm going to match. Now, you have to be careful that this fragment is unique in the sense that to guide the docking, because if I had just selected, for example, the phenyl group, that would not have been sufficient. Let me just select the phenyl group right here, and let me go back to the docking application. Notice right now, there's 2 highlighted regions because MO's telling you that you've selected the phenyl, and on your molecule, you have 2 phenyl groups. So now what it's going to do is it's going to use both of these phenyl groups to guide the docking. So it's going to use this phenyl group to do the placement, and it's going to use this phenyl group to do the placement. So there's 2 options here, all right? So it's very important that when you are running template-based docking, you select the minimum unique fragment within your environment to ensure that the placement is guided properly, okay? And when you do that, you'll see that only 1 fragment will be highlighted. And now with this, I'm confident I can run the docking. So we'll give our docking a name. And then what I'm going to do here is I'm just going to, for just today's exercise, I want to generate a lot of placements and a lot of output poses, because I want to show you, for example, all the sampled conformations that will be run through and evaluated. Typically, you know, for running template-based docking, placement of 10 and refining only 5 structures is usually sufficient. But today, you know, just for the exercise, I'm going to produce more poses so I can show you the diversity that MO can create. So we'll click on OK, and then we'll click on Run, and it says it exists. We're going to overwrite it, and there you go. All right, so now what happens is that after I gave my docked database output a name, so this is the database name, all right, that I provided. And when I clicked on run, it opened up the database viewer. So this is the third major window in MOE. Today, we saw three of them, right? The three major ones. There's the 3D visualizer, there's the sequence editor, that's the second one. And the third major window is the database viewer. So what the database viewer allows you to do is it allows you to visualize MOE databases. Whenever you run large-scale calculations or any type of calculations, MOE will usually write those calculations to a database. And the way we visualize those databases is through the MOE database viewer right here. So as the calculation proceeds, once there is some output, those outputs will be written to the MOE database. The MOE database output looks very much like a spreadsheet, but I wouldn't say the only, but one of the interesting features of it is that you can manage structures within the database viewer environment, all right, which is very difficult to do with a regular database or a spreadsheet like Excel. All right, so let me run through exactly what's going on right now while we wait for the calculation. And let me close my builder and shrink my window to get a bit more real estate here so we can see what's going on. All right, now, and let me just turn off ligand properties and R vectors, remove some of the clutter. Okay, so now when you're running docking in MOE, we'll click on SVL. All right, so right now MOE is running docking, and to keep track of the docking calculation, you can turn or open up what's called the SVL command line interface, all right? So SVL stands for Scientific Vector Language. It's actually a programming language that we use in building all MOE applications. So all the applications that you saw, such as the surfaces and maps, the docking, the protein contacts application, those are all written in Scientific Vector Language, SVL. And it's completely open. You can go, you could look at the code, you could modify the code to your liking, you could change the scoring functions in the docking applications and so forth. All right, but they're written in SVL. And if I click on the SVL button in the MOE window or within the database window, they both will open this panel right here. All right, so let me just resize it. In this panel, we actually print out all the progress of the calculation. So you can see that the docking started on this given date. And then what happened was that MOE started conformational searching. So what this means is that when you run docking in MOE, MOE will take your molecule and it will automatically, if it's not a conformational database that you're feeding in, it will take your molecule and it will generate conformations of it. Right now, it generated 1,000 conformations. It looked for duplicates for those conformations. It found only 95 that were non-duplicates, all right? And then it took from those 95, 25 poses that were energetically favored, and then it placed them. And from those 25, it took all 25, because I insisted that I wanted however many were placed to take exactly that same number and refine them. And then what it did was, upon refinement, it found that there were 10 that were duplicates. And so it discarded those duplicates and it kept 15. And it output those to the database. And that's what we see right here. So you can see there's 15 entries. If I click anywhere on the cells under mol, I can resize the cells. So the docking database looks like this. All right, so you've got entries. All right, each of these entries represent a docked pose. The mol field represents the structure field. the S field over here is the docking score for this particular molecule, okay? And then you have a number of scores that are broken down. For example, RMSD refine, E-score 1 is the placement, E-score 2 is the refinement score, which gets carried over to the docking score. So this is essentially the docking database. If you want to evaluate these dock poses, you can click on File within the database viewer, click on Browse, and this will open up the database browser, and it will display the pose within the MOE environment right here. So you can see that it generated the first pose. So it looks like this. And then if I look at the second pose, the third pose, the fourth pose, the fifth pose, and so forth, okay? You can see that there's a variety of different interactions that are taking place, right? You can see that in some cases, my ligand has actually shifted away from its original position. The big assumption that I made when I modified my ligand was that this quinazoline scaffold, because it was being retained, was going to interact the same way, even though I had introduced this very large, or this aliphatic amino chain. But that may or may not be true, right? It's an assumption that I made. But that's why we have to run docking, because when you run docking, now what it's going to do is it's going to generate conformations, then it's going to take those conformations and it's going to place it within the active site. And then the influence of that chain is going to come to bear on the rest of the molecule. The question is, how much influence does this fragment have over this fragment? And this fragment, I would say, represents roughly a third or maybe 40% of the ligand that you see over here. And so it's quite large. In some cases, the effect is quite large, such that it has moved completely away and I've broken the interaction. So if I just hide my modified ligand, so I'm looking at Tarceva and I'm looking at the dock pose of my modified ligand. You'll notice that in this pose, I don't have this interaction with the water molecule anymore. I don't have the interaction with the glutamine 767. I have weakened the interaction with this hinge binding domain. And also, but in contrast, I've picked up some additional interactions over here, all right? And of course, you know, there's an influence on the docking score, okay? So this is one way of evaluating all the interactions that are being generated and the effects those interactions have on the overall docking pose of your ligand. All right, so that's about all the time I have for today. If you guys have any questions, I'd be more than happy to take them right now. Yes. Yes, Fatima.
Yeah, so I had a question about, so the scores, do they have a unit?
Yeah, the scores are in kcals per mole. Okay.
And then when you open your docking window, there are multiple options for placement and refinement, and then for scoring. Is there documentation which we can go through?
Yes. So all MOE panels, you'll notice the docking panel, the browser, the protein contacts panel, all panels have this question mark at the bottom corner left. If you click on it, it will automatically take you to the manual page that is related to that application. So right now it goes to docking, and right now you'll see computational background, all the scoring functions that are available in terms of the placement and the methods, they're all listed right here. Does that answer your question?
Yeah, I had two more questions, if that's okay.
Yeah, sure.
One of them is, how easy is it to are these tools transferable to nucleic acids? Or
yes. Yes, you can. Yeah. So as I mentioned, but you have to be very careful when you're dealing with nucleic acid, because what we do is the force field that we use is amber 10 EHT. Amber 10 is the protein force field, and EHT is a small molecule force field that we've EHT is a in-house force field that we've developed. It's just that you have to make sure that you have the appropriate parameters for nucleic acids in the amber force field. Usually, I mean, it's pretty good given the state of it, and people use it. But it requires a certain degree of caution. You have to be careful when you use it to ensure that it has been properly parameterized.
Is there any way to add custom force fields to MO?
There is, but it's not trivial. So, for example, if I clicked on the amber 10 EHT right here, what happens is that this potential setup opens up, and you'll see it's under force field. If I click load, these are all force fields that are available in MO right now. So if you want to use, for example, MMFF 94, this is what you can just click on it and it's switched to force field. If you want to use Charm 27, you just select it and you can use the Charm 27 force field. Okay. Sure. Now, to load custom force fields, you can if you click on other, but this requires you to generate what's called a .ff file format in MO, which is the force field file format. And if you click on the question mark at the bottom down here, it will take you to the force field page. You go all the way at the bottom, I think it was force field file format right here. If you click on that, it will describe to you exactly what you need to create your custom force field file. It's not trivial. It requires a bit of work.
Oh, but is there an example? Like, is there a .ff force field file that you could look at?
Absolutely. All the force field files that are in MO are in your MO installation. So if you go to MO, $MO, I think it was in here, amber10eht.ff.
Okay.
So it's $MO lib, and there it is. So you can open these up and you can look at them.
Okay. And my last question, if it's okay.
Yeah, of course. Ask as many questions, and that's why we have the question and answer period.
Okay. So in your ligand properties, you said you customized it to include the pain score.
In the ligand properties, yes. Ligand properties right here. Yes, I have multiple ligands right now, so I just need to turn one of them off. There you go, this one. Yes, here.
Yep. So how do you add things to it? And is there a way to change the algorithm that calculates the log D or log P for? So what you want to do is you want to introduce new descriptors. Absolutely, you can, but that requires you to do some SVL scripting. Okay. You can create your own descriptors. You can, like for example, the pains. This was a method that we took and we evaluated. Just 1 second, please. Sorry about that. So so you can absolutely write descriptors. All you need to do is develop the method. So if there's already a method out there, you can take that method and you could use SVL to script it up and then use it in MO. Absolutely, you can do that. That's what we did with pains. For example, if you go to this site, let's go to SVL, and Mauricio will probably put this in the chat. Yes. You have complete access to this site. These are all MO extensions that you can use. They're not included within the MO software, but you can download these extensions and add them to your MO. I've already done that. See, I have this extra button in my MO. If I click on that, I've got what's called the MD analysis package.
I've got something called doc RMSD. I've got zinc conformation import. You can import conformations from the zinc database. So these are all extensions and scripts that we've got. And then what happens is that if you go to the site and I just type in panes, see, this is the panes application that I downloaded. This is the paper from which we used to produce this panes filter. Okay, so absolutely you can do it, but it requires some of them are done. So like, for example, if you want to add panes, it's not a problem. If it's a known descriptor, it's not a problem. But if you want to develop your own descriptors and you want to include it, that requires you to do some SVL programming, write the script, and then add to it.
Okay.
And if you want to know more about SVL, we provide tutorials for that as well. So if you go to help and then contents, over here, there's SVL programming. If you click on that, it gives you SVL tutorial, more programming tutorial, and so forth. So you could probably follow and try to understand how the programming language works. And since I'm on the topic of programming, the one thing that I want to mention is that just like in Excel, where you have a number of different functions, for example, you want to do summation function, average, net present value, and so forth. You know, Excel has a large number of functions or macros that you can write. MOE has something analogous to it. So we have the what's called functions, MOE SVL functions. These are all the SVL functions that you can use in order to manipulate or calculate and use the atoms or residues within the MOE environment to whatever that you'd like to do. So for example, if you wanted to build a molecule, instead of using the builder, you can say SM_build, and then you would just type in, you know, the smiles pattern with the string, and there you go. It just created a small molecule, which is right here. See, if I go to center, there's my molecule. I just created it.
That's
Okay,
pretty cool.
so you have all those all those options. Does that answer all your questions, Feta?
Yes, thank you so much.
Yeah. Okay. Roy, you have a question?
Yeah, I have a question. When you provided with the docking scores, you provided with all the poses. How to select the right poses? That's one of the things that I've been wondering, because there are, you know, issues with the RMSD values that we have to keep in mind. Not all the top scores are the poses that we are looking for. That's what I understand. And because there's another connecting question to this, when I deal, you know, with the homology model derived docking methodology, a slight change of pose might lead to, you know, a bond change from maybe a hydrogen bond, which was, you know, which I got in a crystal structure dock, you know, complex. It changed into a hydrophobic interaction in a dock complex when I'm doing the same experiment with a model, you know, what we generate. So how to, you know, ascertain which pose to, you know, is the right pose for us?
Yeah. So that's a very tough question. It's not easy to answer, because usually you can't really rely on, let's say, the docking score. So what we've done is when you run docking, we have this option that is automatically turned on. Do you see this? Generate fingerprints. And what this does is it will automatically generate protein ligand interaction fingerprints. And in your database, if you go right here, all the way to the far right in the database, in the doc database that we generate, you'll see there's these three columns: PLIF raw, fingerprint PLIF, and PLIF ligdx. And there are a whole bunch of numerical values in here. These numerical values and more are called vectors. And what they consist of are the information that they encode is residue number, ligand atom type, interaction strength, residue interactions with ligands, and so forth. So we can actually take this, and then if we go to compute PLIF, we don't need to generate it. We need to analyze it because we've already generated it. If I click on analyze, this is what is produced. This is called the PLIF panel, analysis panel. At the top, you have it's a plot, and the plot, the information, the data from the plot is tabulated below right here, okay? So let me explain what the plot is. On the x-axis, you've got all your residues that are interacting with your poses, all right? So this is your protein sequence, but it only represents the residues that are participating in an interaction, right? You don't have the full protein residue. On the y-axis, each line, all right, each line here represents a database entry, all right? So it represents a pose. Okay, so for example, this entry right here, it's this pose. The second line item, it's this pose. Every time your ligand interacts with the residue, you get this black box, all right? Now you'll notice that in all the cases, in all the poses, you've got methionine 769 that's interacting, and you've got this one as well, all right? Now, oh, do I have two? Okay. And then, but for some of the residues, you don't get consistent interaction. In barcode mode, this reflects the database. That means that it's entry 1 to entry n all the way to the bottom, all right? And you can see that in the table as well, entry 1, entry 2, entry 4. The tabulated version tells you the type of interaction. So for example, if I went to methionine 769 and I just hovered over, you'll notice that underneath you'll see double A lowercase. So if you just hover your mouse over the number, it'll give you a pop-up and you'll see the legend. Small case a or lowercase a is backbone hydrogen bond acceptor. When you have a single A, it means that you're picking up an interaction. When you've got two A's, that means that you have a very strong interaction, all right? So that's what the 2 versus 1 means. Now, when we're looking at this, one way to kind of assist in which pose is interacting, what we want to do is we want to evaluate those cluster of poses. So what you want to do is when you're looking at the poses, rather than just focus on, for example, the overall interaction, just the docking score, you want to see if you have very similar or cluster of poses that are interacting with similar residues. And that's what the PLIF will inform you of. If you put it in population mode, then what you can do is you can say, all right, MET 769, aspartate, leucine, MET is important. Let me go look at what those poses are and whether they're very similar to each other. And that will kind of give you a bit more signal as to which poses are representative of binding, of the binding pose, rather than just focusing on a single pose. Because if you just focused on the docking score value going from pose to pose, you might get very different poses. But at least with the PLIF, because the interactions are very similar, because they're interacting with the same residues, the hope is that the poses will be similar. And given the fact that you're getting more sampled poses that are very similar, that means that the binding poses for that particular conformational state might be more representative of how the ligand binds to the protein. Does that kind of make sense?
Yeah, a bit for sure. I just want to add one thing, because there was a valid point that you actually took into in the notice, that there will be similar type of amino acids that will be involved in almost all the poses. My knowledge pushes me to ask you, I have a strong feeling that a single amino acid which is involved in the binding with the ligand is not only capable of forming a hydrogen bond, but it has the capacity to form different types of possible bonds like ionic bond or lipophilic and these types of bonds in different type of poses. Does it make sense?
Yeah, absolutely. I mean, we saw that in the example, in this example, right? So when we were looking at the protein contacts, for example, when we had Tarsiva right here, this Tarsiva, obviously this methionine is implicated in a hydrogen bond, but it's got a lipophilic bond with the side chain of methionine, right, with the phenyl group. So that is exposed. That has, a hydrophobic or a lipophilic type of interaction. Absolutely. The residue can be implicated in multiple types of interactions, not only a single type of interaction. Yes.
Yeah. Can some changes be made in the fingerprint, representation that then in different poses we can see number of different bonds that are possible, and then we can come up with some conclusion that maybe in this type of bond formation in the poses the ionic bond is dominating. So we should really think of taking into account this pose. Maybe this can lead to much better binding as compared to other type of weaker bonds. Something like this can
unfortunately, the protein ligand interaction fingerprints, the types of interactions that we usually pick up are mostly driven by polar interactions. So we're not taking into consideration, for example, hydrophobic interactions. When we're dealing with proteins, then what we do is we include hydrophobic surface contact, because we're looking at contact surfaces rather than at an atomistic level. Because the thing is that when we run protein ligand interaction fingerprints with small ligands, we actually map it to the atom. Whereas with proteins, we mostly calculate contacting surfaces because it's so large. It would be very difficult to do that. And if you go to ligand view, you'll notice that if I just, right now, everything is selected in the table. You see it's blue, but if I select only a single entry, you'll notice that, for example, this particular residue, this particular pose is picking up different interactions. It's showing you the different points of the interactions and the residues that it's interacting with. So we can really drill down all the way at the atomic level and say, all right, you know what? This nitrogen on the quinazoline is interacting with, water molecule W10. This one over here is interacting with methionine 769 and so forth. You see what I mean? So, but yeah, it's very difficult to modify the protein ligand interaction fingerprint because the fingerprint itself was initially written to only accommodate polar types of interactions and not hydrogen bonding interactions. We would have to go back in and rework it. But your idea of including a hydrophobic type is interesting, and maybe in the future we might consider it.
Thank you. Really appreciate it. Thank you very much.
Yeah, appreciate your question. Thank you. Yeah. Suha, do you have a question?
Yeah, just a quick question. So I don't know if you mentioned this earlier, but if you did, would you mind telling me if we can, I see that the docking that we did right here in the trial, the test session has a water molecule. So generally, when we do docking for some of our targets, we try to remove the waters that are present in the crystal structure and then do the docking. Yes. So is it possible to do that in MOE?
Oh, absolutely. Absolutely. As I mentioned, when you're doing docking, you have complete, close the docking, huh? You have complete control over the receptor definition. Right, so this receptor definition right here, you have complete control over it. So whatever you select, let's say, for example, if by default, the receptor atoms are sufficient and you don't want to include the solvent atoms, you just pick receptor. If you want a part of the receptor atoms to be considered, then you have to select those atoms, right? And then create a set, select, set, create. And then you would say, this is my receptor, right? And that will be your receptor definition, which will not include the water molecule. And now if I go to my docking application, I'll just pick, this is my receptor. This is my receptor. This is my receptor, represents the selected atoms right now that I've done. But they don't have to be selected because they're contained within the set. Does that make sense?
Perfect. And just a follow-up question to that. So so this docking that we did was based on a receptor idea. Is it possible to do like an induced fit?
Yeah, absolutely.
Probably that's outside the scope, but I just wanted to know. Thank you.
Yeah, so under refinement, it's induced fit.
Perfect. Okay, thank you so much.
Yeah, you're welcome. You're welcome. And Zico, you have...
the question is, are we going to have access to this recording?
There is no recording, but what we do is we offer this on a monthly basis. So you're more than welcome to come and join. But in addition to that, we do have recordings that you can access. So if you go, for example, to our website, which is chemcomp.com, and Mauricio will probably, actually, I could put it right now. If here, I'll take this page and I'll put it in the chat.
It's already there. Sorry.
It's already.
All right. Yeah, I was on mute.
Yeah, no, that's fine. That's fine. If you go to our products page, so if you just click on products on our website, you'll go to this page right here. And each tile has this option, view the video library. If you click on that, you'll see a whole bunch of different recordings for different applications. So for example, if you want to do covalent docking, template-based docking that I did, if you want to do that, you just click on it and you can visualize it. You can play the video and it will describe to you how to do it. And I think they probably even use the example that I used today.
Correct. Vincent, the reason why we don't record these sessions is because as you yourself right now, you have your camera on, and for privacy reasons, then we should not do that. But like Al was saying, pretty much every single webinar that we have ever done, well, the topic, it's in there, so you can see all those recordings, and then there's a lot of them. There's easily 40 recordings in there.
Okay.
And then if ever you need any help, you can always go to this website. I think Mauricio already put there. So these are most sessions that you can schedule. So when you're here, some basic stuff, let's say you're interested in, I don't know, ligand modeling in the active site, just click there. And then you'll select a date, a time, and magically on that date and time, I will appear. And we can discuss whatever protein you would like to discuss, on your system, using your protein. Yes, Sveta, you have a question?
Yeah. Is there a session available to go over how to use MOE on the cluster or at the backend instead of the GUI?
Yeah, I mean, we can set something up there. It's pretty straightforward. Okay. What type of calculations do you want to run?
Virtual screening, structure-based, like docking through multiple molecules at the same time.
Yeah, I mean, that's really straightforward. Yeah, that should take, I would say, 15 minutes. But what you need to do is you have to ensure that you have you've set up MOE to run on the cluster.
Okay.
So
and that you have enough tokens.
Yeah, there's that too. Okay. So yeah, so there's two things. So absolutely. So the first question is there something to run on HPC? So you want to learn how to run MOE in batch mode on a high performance computing cluster? Absolutely, no problem. So that's number one. And number two, the question is, for us to be more productive during that session, it would be good if your MOE is installed on the HPC and you have enough tokens to run them.
Okay.
because like, let's say, for example, if you wanted to run virtual docking, there are a few things you need to do to optimize running virtual screening using docking, using MOE, because just setting it up and running it is not sufficient. I would highly recommend you generate first a conformational database. There's a few things you need to do before you get to running docking, at a scale for virtual screening. Because my impression is when you're talking about virtual screening, I'm assuming you have like, I don't know, 100,000 ligands or 1 million ligands that you want to run docking on, and that requires some preparatory work. It's not, it wouldn't be just let's pop the docking application. This is my receptor. This is my database. Click run. I wouldn't recommend you do that.
Sure.
But absolutely, you can set something up and we can discuss it, and I'll try to walk you through it.
So the prereq is to have MOE on the cluster.
Well, if you wanna run it, yes. If you want to just do a partial setup of it, and then me describing what you require in order to run it on the HPC, that's possible too.
Okay, all right, thank you.
The question is, there's never a prereq. You're more than welcome to set it up.
Okay.
I'm more than happy to discuss it and guide you through it. And if we ever, come to if there is a barrier or something like that, we'll figure it out. We'll set up another session and then we'll go through it. So don't feel like there's a prerequisite that you need to have something before you set up the session. Set up the session and then we'll work in real time on the fly, as they say, and solve your issues.
Great, thank you.
You're welcome.
All right. I don't think we have any more questions. I'm very happy that a whole bunch actually stayed after the presentation for the Q&A. As you can see, it was well worth it. There's many things that are discussed in these Q&A sessions that are useful for you. Just a reminder, we repeat these sessions every single month. You can join as many times as you want. If you want to join the next one, shoot me an email. I'll send you an invitation and we'll have you there. And thank you, everybody. Thank you, everybody, again. Thank you all for the amazing presentation. And we'll all be in touch. Have an amazing rest of the day.
All right. Thank you, everybody. Bye-bye.
Take care. Bye.